Okay, we have 2 more minutes anyway. But okay, I understand that maybe we will but for everybody to wait. We are going to continue our week. We have two homework classes left, and then we will have a day off, and the next week already will not be doing it. So for these 2 days, I have chosen 2 topics which I think are the key to success, especially at the high-level contests, that are advanced dynamic programming, which is today's topic, and geometry, which is tomorrow's topic. As the previous days, the contests themselves will not be related to topics, the contests for the last 2 days are also a little bit more difficult, I think, than those for the first 3 days. And if you feel, okay, I think that those who feel that it's too difficult for them, they are late for the lecture. But anyway, if you feel that it's useless for you to have more difficult contests, we can set up an alternative for you, but it will not be on that platform, it will be on platforms. So if you need alternative contest, in the end of the lecture, I will tell you what to do to get. But please do not jump between. So if you decide that you keep on the track with harder ones, then you do that. If you decide to switch to either one, then you do that and you return at least today. Okay? Okay, so let's go. And today's topic is advanced dynamic programming. What we will be talking about is the set of optimization for dynamic programming that give you the real improvement of asymptotic. So you have like the naive solution may be running in n cube or n square, and we will discuss a couple of different techniques that allow you to convert that to n maybe a logarithm n, and so on. So really reduce the complexity by dropping some. Mostly this puts some requirements on the formula for recalculating dynamic programming for its source or something else. I will give some hints on how to understand that this or that optimization can be applied, but we will not go deep into details for proving, because of course a few people do prove something at a real contest. But I will give the idea how to understand that it can be proven, which is usually left as an exercise by tutorials as well. Because everybody is lazy, the problem setters as well, so they do not like proving things that they feel it by gut. But however, this sometimes is not so good, because for example, this year in our super regional, like we have Latin American finals, we have Northern Eurasia finals, and we had an interesting opposite situation. There was a problem which was mathematical, which was one of the easiest actually. Most of the teams solved it in the first few minutes, like in the first hour, in the first 30 minutes. It was second or third problem to be solved. It had a simple greedy solution, which is easy to code, and unfortunately was incorrect, although it was proved in that tutorial, but it turned out that it was incorrect. There were the author and the developer of the problem were the mathematicians who came up with a solution, proved it, coded it. It was just like 4 lines of code, created tests, and everything was fine. All the testers also invented the solution. However, on the online contest, some contestants were using ChatGPT. ChatGPT could not invent the solution because it's incorrect. But he invented counter case for the solution, which I don't know, maybe some of you have seen that. So, actually, on one side, proving doesn't save you from incorrect solution. On the other side, on the real contest, if you're not, of course, for the problem setters, it's essential to prove it, but for the contestants, it's more important to understand the direction of that proof, but the proof is not. Okay, while I was discussing that. Most of the people I think have arrived, so let's start. Our first part of the lecture, I think that longest maybe probably part, maybe fourth, fifth, or the whole lecture actually, will be devoted to dynamic programming optimizations. We will consider, start with considering the following optimization. First, we will consider so-called convex hull trick, which is well known actually, I think, and is one of the, I don't know, oldest maybe known dynamic programming optimization. The first program on CHT that I know was at IOI 1999. So actually, the test data for the problem is quite weak, so most of the content, and also there was no online judging at that time, so I don't know exactly, but there is a program we will discuss today also that can actually use that. So an alternative to convex hull trick is the data structure, which is called Lee-Chow tree. That we will also discuss. Another alternative to this is 1D optimization. That is another, we look at this that is another way to use those constraints introduced that allow you to use CHT. This is like dynamic programming from the back, from the forward from the back, and that is forward from the current position. So you will see. Then we will also consider two optimizations related to so-called monotonity of the cutting point. That would be divide and conquer optimization, given sending greetings to the previous lecture. It is actually related to the previous lecture, but I decided to include it in today's lecture, not in the previous one. Then so-called CNUS optimization. Well, it is jargon, of course. CNUS did describe this optimization in his textbook, but I'm not sure that he was the one who just invented that by himself. Maybe he refers to some other authors, but it turned out that it's in his book, so and we will also discuss what is now again jargon called lambda optimization, which I would call 2D 1D optimization, actually following this pattern. Like this reduces two-dimensional problems to one-dimensional. But that is a plan for the first part. Again, this first part is a bigger part, a longer part for the lecture. If there is time for the second part, I will also cover some specific dynamic programming topics that do not fall in any of these general specifications. Okay, so this is the plan. Let's move on. And we will start with the general setup of the problem. That will be our main demonstration problem for all this technique. So most of these techniques actually can be demonstrated all in one problem. The problem is the following. Suppose that you have a line, a one-dimensional line, with some points on it. And you want to cover them with segments. And there is the cost for the segment, and the cost for the segment is its length squared plus some costs, fixed costs here. So that's the cost for the segment NPR. And there can be or can not be another constraint that the number of segments is limited. So if it can be that you can use arbitrary number of segments, or there can be the limit that you can use at most k segments. Actually, this is not a big deal if there is no such restriction. You can just say that you can use at most n segments, and this way you can use. There is actually no restriction because definitely, of course, if C is big and negative, not even big, and there is no such restriction. There's like an idea you can use many zero-length segments, and they make arbitrary negative cost. But of course, it's a special case. So if it's not, so these are either one-dimensional or two-dimensional problem in the sense that if there is no restriction on the number of segments, it's one-dimensional problem, right? And the solution would be like, what is the minimal cost to cover the first, say, I points? Call it I. It's the cost to cover the first I points. And what is the formula to update the dynamic programming? Okay, this is point number I minus 1, the 0 index I. Let's take a look at the last segment. It's the first point that it covers, let it be j minus 1. So it's minimum for j smaller than I. Definitely, like the cost covers points from j minus 1 to I minus 1, from j to I minus 1 inclusive. I not inclusive, let's denote it like this. Plus the cost is this, for example, or that can be actually alternative. So I think that you have seen a lot of problems actually, maybe if you solve some post process rounds, whatever, that have similar formula for the updating the dynamic programming state. So this is what I call backward dynamic programming, because what you do, you are referring to the previous values of dynamic programming DPJ. You can alternatively make forward dynamic programming. There is no like recursive formula in this case, but we say that suppose that we know dp for j for this position. Then let's iterate over possible next segments and update the values for greater values of e of I. So that would be like 4I from j plus 1 to n probably minus 1 inclusive, like dpi is minimum of current value dpi. Initially you wouldn't initialize it with infinities. And well, that thing is dpj plus cost of j. So this is actually the same recalculation formula, but applied in a different order. So here we already know all values for dp smaller than I, and use them to find the value for dpi. And here we all the values for dp up to j are correct, and we use dpj to update all the greater indices, dp for all greater indices, and both ways are fine, but they lead to different techniques to optimize that. So if you have this, you usually would use Excel trick or literal trick to optimize that. If you have this, you can use 1D, 1D. Of course, for such is a program like this, it is usually almost equivalent. You can write this formula, you can write this algorithm. But sometimes one of these methods is much simpler than the others. Because, for example, if your the reason can be, for example, calculating this cost. Calculating this cost involves some like process, like simulating something or whatever. It can be sometimes easier to move forward, like going not calculating this for every segment independently, but starting with A and then adding point one by one and updating for the usual case for this. And in this case, for example, getting back might not be easy to do because in this case you're adding something to the beginning of the process and it is not easier updating. Sometimes this method is easier in the setting of the problem, or sometimes it's the only one. Okay, this is one-dimensional problem, but there can be a two-dimensional problem when the second constraint is introduced, which is the number of segments that you can use. In this case, you need to put that number of segments into your dynamic programming, so this formula becomes like dp I t, like t is the number of segments. Actually, usually you would use t as the first index, pti, it's count of segments. And the reference is essentially the same, but now you reference here the pt minus 1 because you have one segment less. So like minimum for j less than I goes j to I again plus dt t minus 1. What is the difference except that you have now you're now multiplying your complexity by the number of segments that is k. The difference is that you would also need to not need to on the contrary, you not don't need to go in any particular order on I because you're only referring to the previous row of your dynamic programming here. You can update the values for I in any order you like, and that sometimes can lead you to optimizing your solution, which we will see in so-called divide and conquer. Okay, and also what we will see is that in some cases you can make a reduction of that two-dimensional problem to one-dimensional one by some smart trick of lambda optimization, but it's not always applicable. So there are some restrictions and there are some nuances. Okay, let's before moving to optimization, the final note. Let's see what is the complexity for these named solutions. In the one-dimensional case, it's clearly n squared of one from them. You have n values and you have n steps to calculate each value. And in two-dimensional case, it's n squared times k, because again, you have now k times n values, and you have n options for each value. Well, before moving to the optimizations, before moving to convex half-frequent geometry, we will need some geometry. Actually, geometry is the topic of tomorrow's lecture, but this geometry will be easy. So the only thing we will need is to intersect lines, and also not like general lines, but even so called in Russian high school lines that are like in the university when you're discussing lines, maybe a computational geometry or like, I don't know, just analytic geometry. The line has different equations, for example, so-called uniform equation, which is ax plus by plus c is 0, like this. Yeah? But again, I don't know what about Latin America. In Russia, it's put in schools. Lines are considered in the context of the graphics of functions, of linear functions. So in high school, they are teaching that the equation for the line is y equal to k times x plus b. So this doesn't give you the vertical lines. Only any non-vertical lines can be given by this equation. The vertical lines k is infinity. So we are always struggling with high school students when they come to extra classes or programming. No, like when you are in the programming, you will use this higher education lines, but since they will have like exams and like control works and tests in high school, they also cannot forget this one. Now, at school, you do what they do, notice you do what we say. Okay, so now, but we will like go to Russian high school for a moment and use these lines in our today's topic. So what we would need to do, we would need to intersect such lines. It's actually quite easy. We have two such lines. One is like this, and another one. So this is y is equal to k1 times x plus b1, and the other one is k y 2x plus b2. Then, to find the intersection, we say that y is the same, so it's like k1x plus b1 equal to k2x plus b2. And also, from this we say that k1 minus k2x is b2 minus b1, and that gives us the value for x, which is b2 minus b1 divided by k1 minus k2. This is an easy thing, and also sometimes we would like this to be integer, which is also easy. You just round that, or if those coefficients are stored as integers, this goes with integer division, and again, if it's truly integer, you get that correct integer. If it's not, you get like plus minus less than 1 value. For that, it's rounded by integer division. It's also clear you can understand that if k's are the same, so if these lines are parallel, then there is either no intersection point if p's are different, or there is undefined intersection point, the line just coincide if p's are also the same. Unlike uniform equation where you can multiply a, b, and c all by the same value and get the same line, no lines in this representation have unique coefficients because they are like implicitly already normalized. The value, the coefficient of y is forced to be 1. So there is no alternative representation. Every line is unique. Okay, the value of k is actually the value by what distance does the line travel in y-axis if it travel 1 in x-axis, and that is called the slope of the line. So the bigger is the slope, the more vertical is line for the positive slope, and the smaller is the negative slope, the more vertical is line for the line. And there is like this plus infinity minus infinity. 0 is horizontal, are horizontalized. At plus infinity and minus infinity, they are meeting there at the imaginary point of lines with a infinite slope that are vertical, that are not represented by this. Okay, what do lines, especially these strange high school lines, have to do with dynamic programming? Actually a lot, but again, before moving to that, let's solve the following problem for these lines. So we have a set of these lines, like y is k I x plus I for some set of i's. And we have queries. The query is the value xj. And the answer to the query is the following. Suppose that you draw all these lines on the plane. One, two. And what you do is at this point, xi, xj, you are considering this vertical line in this with this coordinate, and find the lowest or the highest. It's actually symmetric. Let's say the lowest point of intersection of these vertical lines and our line x equal to xj. Again, this blue line that I drawn does not exist in our world, so it's the query. And so no line can be, for example, parallel or coinciding with it. So in this case, so this is the query. We will now consider two ways to answer these queries. Again, the set you have a number of lines, you have a number of queries, and for every query you need to find the lowest point among all these lines. So your task is to find the minimum value of kixj plus bi for all available values of I. The first solution to this problem, which is known as convex hull trick, actually it becomes the trick when it is applied to dynamic programming. Now it's like the lower, or if we are looking for some higher hull of the lines. What is the lower hull of these lines? So let's see. If xj is very small, like it's infinite, it's minus infinity, what is the optimal line for this to minimize this value? Since xj is minus infinity, d doesn't matter very much, and the k we would like to be as big as possible, because as great as possible, because it is multiplied by minus infinity and becomes as small as possible. So at the minus infinity there, the optimal line is the one with the biggest k. But at the plus infinity, the same argument gives us that the optimal line is the one with the smallest k. Because it is now multiplied by positive infinity, and we would like to multiply by the smallest possible. B again doesn't matter. What happens between those two? So the maximum slope line is optimal there. The minimum slope line is optimal there. What is optimal in between? Okay, in between there are some interesting things that can happen, like there can be other lines getting better. So this set of optimal answers for all possible queries is called the lower half of our set of lines. How can we find it? Again, which is the first candidate to become better than our maximal slope line as we move from minus infinity to 4. Of course, this is the line which has the next possible slope, then the next, and so on. Well, in this picture, it turns out that all four lines touch the lower hull. It's not always the case, of course. Line that never, that sometimes becomes better than our initial maximum slope line, but actually too late. Other lines are over. So what are we going to do? We're going to use an algorithm that is similar to that for Biblion convex hull. You might know Graham algorithm. Who knows Graham algorithm? Oh my God! Please lower your hands. So maybe we should have switched. Well, okay. Okay. Anyway, who knows Graham algorithm? It will be easier for you, but who doesn't know, it's still the algorithm is simple. So just follow. Okay. So first of all, let's sort our lines by decreasing of the value ki. This is by decreasing of the slope. That is exactly what's gonna be with this lower. Now what do? We have the part of the slope with all the lines that we have already considered. Initially we consider only that line with the highest possible slope, the greatest possible slope, and it is optimal until infinity. So it's like we will use the data structure called stack. Oh, you know it persistent stack already because of our lecture. So you definitely know ordinary stack. Maybe you don't, but it's like in functional programming and Gonada, you know how to make stack persistent, whatever is stacking. Okay, I believe in that. So we use the stack and we put it like so. We don't store the leftmost point we get minus infinity because it's always minus infinity. At minus infinity, the line with the maximum slope is always optimal no matter what we convert. But until what point is it optimal, that is what we store. And initially, suppose that there were only this line, in this case, it would be optimal until the end. So our line number, say 0, is optimal until plus like this. So we put this pair to the stack, and that is the initial state of our stack. And our ongoing state of the stack will be the part of the lower hull with all lines already considered. We will consider them in order of decreasing. Okay. So for this picture, for example, if I have considered some several lines, it would be like this. For example, these two. Should there be no this line and this line, the hull would be like the lower hull would be like this. But if we are adding another line with a lesser slope, then what should we do? So this line definitely becomes better than this line at some point, because at plus infinity, the smaller is the slope, the better. And this line has smaller slope, so at plus infinity it will definitely be better, so it becomes better somewhere there. Where? Okay, their intersection point. We know already the formula to intersect two lines, it's very easy. So we calculate this intersection point. Now there are two options actually. One is shown on the picture, and that is this point. At this point, this line on the top of the stack is optimal. Now, in this case, it becomes optimal not until plus infinity as it initially was, but until this point only. So we replace it with a, I will show like this. So we replace it with the intersection point, x intersection, and we push the new line our current I, and infinity to the stack. The new line is better until the end. And that previous line only until the intersection. That is one case. Another case, that happens if, for example, this line is so good that it actually overrides totally the segment of optimality for that line on the top of the stack. If this intersection point is even what we would like to keep on the stack is this lower half. So these values until which point the corresponding line is optimal, they should be in the increasing order. If putting x intersection here would damage this order, we deduce that this segment is never optimal at all. The segment of this line is never optimal at all. So we just copy it from the stack completely and move to the previous line in our case. So the code looks approximately like this. We consider lines one by one, starting from the first one, the zeroth one is the initialization. We take like j from the top of the stack, the second value, not first, because we wouldn't, the second would, on the top of the stack, the second value is always like plus infinity. So now we make an intersection of points using the high school formula. Then we see, we take a look. If there is nothing in the stack, so this was the first line, so it's from minus infinity, or on the top of the stack, the current value, which is the beginning of the optimality for the jth line, is smaller than x intersection, then we return j, but with the reduced segment now not until infinity, but until. And move on. If it's not, then we do not return j, but go to the previous line. So it's like the cycle. While something, if stack is empty, or top dot x is less than x intersection, then we push j with an intersection point, but push and break. Else, okay, it's popped and go on. Open another one. And after this, we always push I with plus. So that is how it goes. Okay? Clear? More or less? The code is quite simple, as most such stack algorithms, like both comics, how it is not very convenient with the language while cycle because it's exit in the end or in the middle. But okay, I hope we can deal with it. So this creates this lower half. How can we now use that to answer the queries? So we have the query, and we have the lower half in the stack, which actually, since we are using, STD vector for this stack, can then be forgotten that it was a stack, and just become the array of segments that form this lower half. So in this case, if we have the query, we just direction children. If we want to separate the process of creating lower half and queries, then okay, we have created the lower half. Now the queries, we can use binary search for every query and process them independently. This x values form the breaking points of this polyline that forms the lower half. So we just find which segment corresponds to the wiring. For this segment, we have the number of the line that is optimal at this segment. And from this line, we can find the wiring. Another option is to sort the queries and to make like a two-pointer algorithm. We are going to query, if the queries are known before, we can build the lower hull and then process queries one after another by going in parallel by queries, and if the query goes to the next segment of the lower hull, then we just increase the index of the lower hull segment. Use the 2 points. What if the set of lines changes? What if lines are added to the set, or in the worst case removed? Removing is actually not important for dynamic programming, so we will not consider removing, although it can be great using in offline setting, for example. It can be similar to what we have discussed before yesterday. If you remember dynamic connectivity offline, the same technique can be applied to like lower hull, dynamic lower hull offline. This step we don't do, except for the degenerate union, we don't do the same. But in dynamic programming setting, usually there is no removing, but there is adding. How can we deal with added lines? There are two options. One is if the lines are always added to the end of the sorted order. So every new line has its slope less than all the previous lines, or at least less than equal, right, or less. In this case, what to do with lines with equal slope? Actually, if there are several lines with the same slope, for the minimum value, only one of them is okay. It can be good. Which one? For the smallest value of b, yeah. One of the smallest value of b. So, if we are adding line to the end, then okay, we can progress with our algorithm. So, we just wait. This 4, what's inside this 4, we rename as it is a function, say f line. So here, for example, well, if the lines are still indexed, we can use push j and I. Here, if the lines are not indexed anymore, then we can push the reference to this line. Not so important. So this add can be, if the lines are not being added in the increasing order, if they're in random order, well, okay, the convex hull algorithm still can be updated to deal with that, but actually, just like you need to go to two directions. But it's not worth it, because our next data structure, which is called the chow tree, will handle that automatically, and no need for special geometry like tricks. So okay, if lines are constant and they are not added, or if the lines are added in the order of the decreasing order of slope, then we can use this. What is the complexity? The complexity of stack is linear, of course. So for answering the query, if queries are random or online, then the complexity of the query is logarithmic. If the queries are offline and already sorted, then the complexity for the query is constant. You just use 2 pointers, so answer all the queries is n plus. Okay, so and how can we use that for our TP? Let's take a closer look at what we're having here. DPI is the minimum value for cost plus dp. What is the cost? When we were writing this formula, we used like abstract cost, and cost. But now we will remember that cost is not arbitrary. Cost is particular, and it is length squared plus the constant. Let's write it down. So how do we calculate this length squared? Okay, we have these points on the line, and they have coordinates. So the length is actually the difference of coordinates of the endpoints of the segment, and definitely the segment shouldn't be longer than the point that it covers, so it must be fitted with this point and this point. And so this cost is actually, so TPI is minimum for j smaller than I, x like I minus 1, I minus 1 minus fj squared plus c plus dpj. Okay, let's expand this square. We will get this. Minimum j smaller than I. Of what? Here in this expression, there are actually three types of terms. Some terms only depend on I, or even on nothing, like C. Those terms do not actually participate in minimization. It doesn't depend on which j we choose. Anyway, we get the same value for those terms that only depend on I. So let's move them out of minimum at all. It's xi minus 1 squared and this value of c. So it will be outside the I. Then there are some terms that only depend on j. Those terms cannot be, of course, moved out of the minimum function, but they are not interfering with I, they're always the same. So we will combine them. So in this case, it's dpj plus xj squared. So this is what only depends on j. And there are also terms that depend on I and j, both on I and j. And for those terms, the condition so that we can use a convex hull trick is that they must be in a form of something that depends on I multiplied by something that depends on j. So in general case, if they must sum like alpha of I times beta of j plus gamma of j and plus delta of I, which is outside of minimization as well. So if it is the case, we can use CHT. If it's not, some other more advanced algorithm like 1D can still be sometimes used with given some additional constraints, but CHT cannot be directly used. So maybe you can like transform the formula or add some additional parameter to convert it to such form. In this case, so in our case, this is minus twice x I minus 1, which is alpha in the terms of the general segment, times xj, which is beta in our general segment. Yeah. So let's look closely at this and see that if we introduce lines, line number j, which has the form y equal to beta of j plus times x plus gamma of j, then this minimization is exactly the problem that we have considered on this left whiteboard. We have the set of lines, and we have the query x equals to alpha of I. In our case, well, minus 2 can go to xj for convenience actually. So x, so let's do this. So it's not very important, just more easy 2 times minus 2. It is easier than, in a sense that slopes will be decreasing as we want, and squares will be increasing as we want. It doesn't really matter, but it will be consistent with our previous presentations. So x is a of I, and the line is like this, and the problem is exactly the same. We want to find the minimum intersection point of the vertical line in the query and the given lines at the plane. Like I mentioned, here we have non-static situation because J doesn't go to N. J goes to I. That's partially because the B for the line is dpj plus xj squared, and dpj is not known yet for greater values of j. So after this, we have the new line with I that can be added to this set of lines, and then we will move to the next line. So the organization of the code would be this. So I from like 1 to minus 1. What we do? First, we must solve this problem to find the optimal value. So we answer where in T for x I minus 1. And what do we do? And then we add line like what is that? Minus 2x minus 1 and dp I plus x I x plus minus 1. Should we do? What is our? We have actually line number x minus 1, so we will it and yes, okay. The new line that will correspond to I will start at this point, so it's okay with xi. So we have new line like minus 2xi, which we haven't looked at yet, but it will. That is what will be for the next spiral, so that's okay. And the dpi plus xi squared. So these are the coefficients. These are the coefficients to our CH. Since we are considering points in the equation of x, the lines will be considered in the equation order of slope, which is just what we need. So that would work. And also answering queries can be made so that there is an average of constant time per query. The only care that we should take is that actually the queries would change if the set of lines would be constant, then that would always be going along the stack from the beginning to the end. But since it's not constant, the stack itself changes, and it can turn out that our current index in the stack was popped. So when we are popping, if our current index and answering queries is pointing to the line that is popped, so it must be decreased by 1. And it can then increase by 1 again because but it must be, you must be accurate with that because you can, for example, the new line comes like this, so a lot of values are popped, and it's kind of out of range for out of range access to this. Okay, so if you do this, then the total complexity is what? If we ignore sorting, for example, just points are already given in the sorted order, and then that would be linear time, because both answering query using the pointer and adding line using the stack works in a more nice function. Well, okay. Any questions so far? Comments? Okay. The next thing that we're going to consider will be alternative way to do the same using the data structure called leach-out tree. The situation is the following. Leach-out tree has advantages and disadvantages. One disadvantage, there are two disadvantages from my point of view. First, it is very simple, very easy to code, very easy to understand. It is simpler than even this. This is quite simple algorithm with a stack, but still it has some geometric intuition. It has some dangers like accessing empty stack and so on and so forth. Leach-out tree doesn't have all this property. There is a constant segment tree structure that can be easily updated, and it is easier to code, in my opinion. Although, for myself, choosing from all those algorithms that we are considering today, I would actually use 1D, which is the most universal application. But okay, we will get to it a little bit later. Now, another advantage is that it doesn't need to add lines in the order of within the slope. Of course, the authors of the problems have created like 20 problems on standard CHC, and then started to invent cost functions so that it decomposes like this, but the values of Vj are not created in order of importance. So you can imagine alternative cost function for the segment so that it introduces some randomness here, like, I don't know, plus xj modulo something or whatever, and that forces it not being still decomposes like this, still the line trick seems to be possible to be used, but now this operation at line becomes more tricky. And this is the advantage of CHC or of leach-out tree, that it is it avoids that. On the other side, there are disadvantages. The main disadvantage is complexity. In this case, we have n, and leach-out tree makes wiring, both adding and wiring, in logarithm. So it will be n logarithm n if leach-out is used. CHT we have. And for leach-out, you will say that logarithm slowdown is not so important. Yes, but no, actually. So because, for example, in IOI 16, there was a problem that combined most known dynamic programming optimizations, A and E. So, and this logarithm was the cost of the last subtotal, so like 17 points. And the lucky IOI people, they just got 87 or 83, I don't remember exactly, and were happy. But you, unlucky ICPC people, would get like time limit exceeded. So that's the so knowing all the techniques, both the common result trick is the most primitive, but the fastest of the optimization. So if you are not very tight on time, other optimizations like 1D or leach-out can be used with simpler code and more flexibility. But if you are very tight on time, you sometimes have no option than just to use the whole plain CH. Now, what are we going to do now? Consider leach-out tree. Lichao tree was, start with the name. Lichao is the name of the Chinese high school student. If you know, how can you get to IOI? By the way, has anybody been to IOI ever in your national delegation? Great. Great. So, how did you qualify? You probably wrote your national impact and won it and were selected for this. Yes. Maybe some of you have also passed through some selection camp. In Russia, we do selection camp. In China, they have the selection camp, which is very intense actually. During this camp, they not only have I don't know, 6 or 7 selection contests, but they also must invent new algorithms. Every Chinese high school student must invent new algorithms to go to IO. Of course, usually this is just interpreted as they must come up with a problem and invent the algorithm to solve it. But there were 2 cases when this algorithm invented for qualifying to IOI from China came into general use. Maybe more than 2. I think more than 2. At least 3. One is Mole algorithm for square decomposition. Maybe you have heard about that. Mole's algorithm. The second is Lichao, which we are going to. Then a couple of segment bits, 3 bits, and its variations. Most of the variations were also from that source, invented for qualifying to IOI. Sometimes, by the way, sometimes they cheat. Once we have reported to the Chinese coach, we exchanged a problem with them, and those problems prepared in this by the high school students for qualifying, demonstrating their algorithm, are also given to other students at some events at this camp. I don't know exact details, but they're exchanging with Chinese coaches, and once we got the problem from our original ICPC contest in this exchange. So the correspondent student just took the problem from our regionals and said that he invented it and gave it as a new algorithm. I hope he is okay. Because we reported that to the Chinese college, but I hope he is okay. Just not taken to IOI. Okay, so let's now getting back from the funny stories to the algorithm. What is Lichao tree? Lichao tree, it can be explicit or implicit. We will start with the explicit one. Explicit one requires that the future queries are known ahead of time. It is in dynamic programming setting, this is usually the case. So if you look at this formula, this A of I that only depends on I, since it doesn't depend on what we have calculated in our dynamic programming before, usually it only depends on I. We can calculate those A of I, alpha of I beforehand, so these are our future queries. And in our this canonical program, they are just coordinated. So let's do this. Let's build a segment tree on these queries, and the contents of the nodes of the segment tree, we will describe later. Let's build it like segment tree structure. 0, x, 1, x, 0, 1, x, like u minus 1. We have queries. Few of them, and we build the segment tree. Oops. So what are we going to store in our nodes of the segment? We still have the same problem with lines. So we have set of lines of the form kix plus ui. And the queries, for the queries, we would answer the minimal possible point of intersection of the corresponding vertical line with the set of the given lines. Queries are the same. What we're going to do, we're going to store lines and at the nodes of our segment tree. Lines. And we want to have the following invariant. We want to do this. Suppose you're answering some query. You walk from the top of the tree to the corresponding leaf of the tree and just put that value of x into the lines that you meet during this descent and choose the minimum value, and that should be the answer. So again, the invariant is that the optimal line is always on the path from the root to the list. The optimal line for that leaf. The optimal line for each leaf is somewhere on the path. No additional restrictions, so in some sense we should put these lines to these lines. How can we do that? Well, the operation that is supported is add line. So, of course, the queries are also supported, but the queries are just descending and choosing the minimum value. So it's clear that queries can be answered in logarithmic time. How would we do update, add line? And what is the initial, by the way? Initially, we would like to put some lines there, which were some neutral line to all nodes that is worse than any line for it at any point. How can we come up with such line? After careful consideration, you can see that this neutral line will be y equal to 0 times x plus infinity. This is very bad line. It is horizontal but infinitely high, so which is worse than any real line at any point. Of course, the exact value of infinity you should choose depends on the problem. Okay, so now we're writing the line. So in the process of adding, we will be descending the tree, and our temporary invariant will be the updated one, so that we have the line on hold. And we have the current vertex. And then updating invariant during the process of adding a line would be the optimal line for every leaf is either one of the lines on the path from this leaf to the root, or if you pass the current vertex on this path, it can also be the line on hold. Initially, we just make the root the current vertex, and the new line is on hold, so the new invariant is not correct. And then we will descend until either our on-hold line becomes useless, or we go down to the leaf and work there. So anyway, in any of these cases, finally we get rid of the on-hold line and restore the original invariant. So okay, let's say, so we are at some vertex of the Lichau tree, and we have two lines there. One line is the one that is now at this node. So this is the node. The node of the segment tree corresponds to the segment of queries from L to R, and it has current line like kx plus b. And our new line, on-hold line that is coming from the top or from the update query, is say k prime x plus b prime. So let's see. Let's draw the picture. So we have like these points xl, xl plus 1, and so on. xr minus 1. There is also the middle of this. If it's the leaf, it's a special case we will get to a little bit later. If it's not the leaf, there is the middle of the segment, like x m minus 1 and xm, so xr minus 1. So this goes to our left sun, this goes to our right. Now, since two lines can only have one intersection point, there are several options actually. These lines can intersect in the area of the left sun, intersect in the area of the right sun. They can also be parallel or intersect outside of the area of this node. In those two cases it's easy. So if they intersect totally outside of the area of this node or are parallel, then at the whole subtree of this node, one of these lines is redundant, the one that is higher. So we just can stop here. If we start, well, actually here is the point. I am giving you some facts. Most of them will not be needed in the real code. They will be automatically processed by the general case. The general case code for the chart is simple and surprisingly universal. So it just works. But when trying to follow the line of thought, we see that there are these cases, in each of these cases, we actually understand what to do. But there is no need to do this, because it will be automatically covered by the general case. So if you are given the if you are creating the concept, maybe you should make a small pause and then just write down the final universal. So okay, if it is if they intersect in the area of this node, then for one of the halves, one of the lines is still better. So let's draw this picture. So I will draw the old line that is in this node, the red one, kx plus b, and the blue line will be the one that is new one, p prime, plus b prime. So like we have the old line and the new line. And at one half of the, at least in one sun of the current node, one of these lines is always better than the other. And in the other sun, there is uncertainty. So let's do this. Let's choose that line of those two that is better in at least one of its suns. Save it in this node. And then go down to the other node with a line on hold, the one being the other one. Because this one, for example, in this case, the blue line, we will keep it in this node. So it will cover the whole right sun and those squares in the left sun that it is still better. So the red line should go down to the left sun. That's a line on hold, because for some nodes it can be better, and if we drop it now, then some wires would be absolutely correct. And the reverse, if the the red line would be better than this one. Now, okay, which line is better and at which side? That is the question. Let us answer it in two steps. First, which line is better? The simple answer is, let's look closely at the picture. If you take this separating line, which is separating left sun and right sun, then no matter if the intersection point is on the left or on the right, the line that is lower on the separation line is better on that side where there is no intersection point, since the other line cannot override it there. The intersection point is on the other side. So where would we put this separation line? Well, like between xm minus 1 and xm any point. For example, let's put it at xm. this would also generalize actually to the leaf. So what do? We see if the new line E prime xm plus B prime is better than kxm plus b, then the new line is better. If it's not the case, then the old line is better. If the old line is better, that is great. In this case, we just go down, keeping this line as is. But if the new line is better, then it should be stored in this node, and the line that was formerly stored in this node would be the line on hold. So in this case, we just swap them. I mean, including that where this KB is stored in the node. So we swap with the actual line in the node, not only with the local variable that holds these values, but with like really true variable that store this K and P. Okay, this is the first step. Now the second step, we must decide to which node should we descend with our line on hold, which is now again T prime, B prime, no matter what it is. Let's see. So consider this point. At this point now we know that K B line is better. So will it override our new line? Will it intersect with the K prime, with the prime line on the right or on the left? That depends on the relation between their slopes. If the slope of the line that is staying, the red line, no, which is what is staying. It's better. The picture doesn't correspond to our code now. So after this swap, this chain line is always the red line. Yes. So if it is the case like this, if the slope of the chain line is less, then the intersection point is on the left. If it's greater, like this picture. So at the just better here, but on the right, the new line will be better. So this means that if K is greater than K prime, like in this case, then we go to the left. Else, and that's it. So as you see, we didn't even need to intersect our lines. Like CHT, Lichao doesn't even intersect the lines. Unlike again CHT, which uses floating point for intersection lines and those values in the stack. I told you that sometimes you only need the rounded integers. For example, the quires are integers, so it don't really matter 1.1 or 1.3 is the final point. You can round it down to 1 inclusive, for example. And for 1, the previous line, for 2, already the new line. But here, even that is not needed. We don't even intersect our lines here. So the only thing to be careful of is that it's about leaves. But for the leaves, M is equal to L actually. So we just keep for the leaves the line that is that is better than that leaf, and no need to recurse of course for the leaf. So this is the code. If there are equal values of K, it adds like 2 lines. So for example, if K is equal to K prime, then we just store the line with the better K here and don't recurse at all because I will do. But so like if greater than if less, and else just don't. Okay. make it like that. Right. Else. Okay, so when choosing from CHC and Licha, if you have non-monotonic headlines here with K, you should always use Licha or some other algorithm because CHC doesn't work with that. If it's monotonic, if you are tight on time, then you should probably use CHT because it's linear. If you're not tight on time, and if you're familiar with Licha, you should try it maybe in some practice and getting it into your team notebook. Then for me, the child code is more powerful and simpler and doesn't have floating points. So I will do that. And what I would also do now is I would start the coffee break, but please be back at like 10:10 because we need to go through a lot of other optimization. They are short to describe, this although geometry, but still we definitely need them all for this stuff. fuzz and sh. Okay, so again, we have covered only two, but the most like difficult to get approaches because of the optimizations, because they didn't like the geometric setting in this line. The next few will be shorter to describe, so don't be afraid so much. We won't be describing them until dinner, only until lunch. Well, and the way of the content. So, first of all, in the break, we have discussed, we have a small discussion with some of you, and it doesn't really easily work for CHT, the idea of GCP offline, because of the amortization with the stack pushes and pops. So maybe, but on the other side, since in Lichao tree everything is true time value, actual time value, so there it should definitely work. So probably you should, it's Lichao tree with undo, not stack with undo, that can handle line adding and removal. Okay, so now the other thing that I want to mention is that we built so-called explicit Lichao tree when we had queries beforehand, that we built that segment tree based on those. However, sometimes you don't have queries beforehand, so you would like to create them as they come. So what you can do is similar structure to implicit segment tree. You create only the root initially for like minus m to m, or whatever m you have, like 10 to 9 or whatever. And then you only create nodes when you need them. So when you have the query, you start from the root, and as you can see in this code, well, if you create the node in the, if you add the line, you only descend to one side, so adding line will create like a row of logarithm n vertices down to the leaf corresponding to just one point. And the query will also create the row of the nodes to the leaf of this query. And when you create the node here, well, it is clear what to create. And actually, when you create a node, you can drop your line and hold into that tree. Don't need to create the whole line. And if you're making query, if there don't exist the new node, and then again you can ignore to create this node, but better. Because if you create all these nodes down to the end, they will have this neutral infinite line. Okay, the neutral infinite line, which is actually not needed, because it cannot improve your results. So you can again stop when you can't go there, because there are those neutral lines actually, and those not yet created. That is what you can do. I wouldn't say that it is much more profitable and convenient than explicit one. So I would, if you know queries, I would use explicit one. But if you don't know, it is not that everything is failing, you can use the implicit one. Well, now, what we're gonna do is we're gonna consider another optimization with the same setting, but with a different subtraces, with a different approach, not the backward dynamics, but forward dynamics. And also, this approach doesn't require this exact decomposition of the cost function. However, it still has a requirement that it can be used. What I will do, I will tell you about this approach. It's called 1D1D optimization. then I will tell you the intuition when it can be used. For example, it can always be used when CHT can be used, but it can sometimes be used even when CHT cannot be used. And the formal inequality that allows to use it in this proof, as I say, we leave as an exercise for your homework. So you can Google for 1D dynamic programming optimization and find it. So let's again. So the setting is the same. So I will keep it. So let's not only let's give the code for the forward optimization in this case. Oh my god! Okay, no problem. Let's give the code of the forward calculation for DP in this case, and additionally, not only store the values of DP, but also let's store the parent values that allow us to restore the answer itself, to restore the segments how should be created. So this code would be like this. So we go forward, so the initial value EP 0 is 0, like 3 to cover 0 segments, and then we go for I from 0 to n minus 1. And what we do, we have covered I, like, well, we call it J, like in the picture. J, we have covered J first, so summon with J to I minus 1, or I from J plus 1 to n, we cover n from J to I minus 1. So if EP I is less than, no, it's worse than EP plus cost from J inclusive to I not inclusive, then we update that. EP plus this cost. And as I mentioned before, we now save the from or the parent value. We say that this optimal value was obtained using the segment that started at J. So we say as parent for I is J. Well, this is a usual technique to restore the answer in dynamic programming problems, okay? Again. So, our close attention now will be that parent array. Let's look at it. So initially, after the first step, when we run J equal to 0, of course, the DP was initially initialized with infinities. So now these infinities were replaced with some cost value with one segment covering from 0 to this point. So this parent array will be filled with zeros. Like this. But what goes there? When we are trying to go from 1, for some points, it will be optimal to go from 1, and for some points, it will be still optimal to go from 0 to that. So the condition that allows us to use 1D1D optimization is that this array parent is always non-decreasing. So it's that every new value parent I plus 1 is greater or equal than parent I. For example, it is not always clear that this is the case, but usually the intuition is that it is, because if the cost function is natural, like our length squared plus like that cost, it's usually clear that if this is the optimal solution for I with the last change, and the optimal solution here would be like this, then cutting down this part and instead introducing this would be better, or on the reverse, cutting down this part and adding that to the previous segment would be better. So, writing down formulas, you can see that for like, not the correct term, like for normal cost function, like for usual cost function that are not involved in some clearly non-monotonic functions like modulo, like given in the input coefficients for cost or whatever, in which case, of course, it can vary randomly. If it is based on like some linear or quadratic or polynomial with positive coefficients function, then it is usually the case that these terms are improved. So this is, in some sense, similar to what we will also consider in a few minutes, like with the monotonicity of the cutting. This is a more strong condition than the monotonicity of the cutting point, because this requires this not only be the case in the end, but for all intermediate states of the array as well. But again, for normal cost functions, it's usually the case. Or there is formal condition. I will write it in the end after discussing that. Like it's called quadrilateral inequality, like that. But of course, again, like it's almost similar to like concavity, I think, of the cost function, like the parabola is going like concave, so if the cost function is like concave, then the quadrilateral inequality follows. It's not the reverse. So there were, for example, I think at ERT in Europe we have a high school tournament called ERT, International April Informatics Tournament, it's organized in Bulgaria for Eastern Europe mostly, and there was a program, no product and no concavity, but the quadrilateral was, and this is where 1D became popular in high school in Eastern Europe. Okay, so let's get back here. So what do we want? So suppose that for some reason we decided, we guessed, or we proved, or we like assured ourselves that this is the case, and now we're going to try to use it. How can we use it? So suppose if this condition happens, then after considering j equal to 1, how can our array of parents look like? So since it's monotonic and after j equal to 0 and 1, there are only two possible options, 0 and 1 in this array. We can only have like zeros up to some point and then ones. How can we find this point? How can we find this point? Binary search. Let's binary search for the position so that for the smallest possible I, such that relaxing the segment from 1 to that point is more optimal than relaxing the segment from 0 to that. So this is then, if we find such point, it is more optimal to put 1 there than 0 as a parent. And since we have this condition, then it is optimal to continue once after that. So instead of this 4, we can use binary search. At this point, I sometimes ask the students that I will do for you as well. And how can we, okay, we have found this point, how do we fill the tail with ones? Okay, please give the answer.
A Q?
Hmm?
A Q?
A Q? What
Say you
the
can
Q?
start in an array and then after you like take the next array.
Well, sometimes the students start to invent something like the array with mass assignment operations, like segment tree. Of course, it will not be needed. As we go on, we will see that actually the step similar to CHT, but without geometric interpretation will be used here. So a similar idea to that. So we don't store actually this parent array explicitly, but we only store positions where it changes between the consecutive values in the stack. Okay, so but let's ignore this was like look a little bit forward, but let's ignore this for a while and go on like next iteration. Now we have 2. J equal to 2, and now actually it's not that straightforward as from going from 0 to 1 because there are 2 options. Either relaxing from 2 is optimal somewhere in the end of the array. Actually, it's usually not the case, of course, because you see it's n, and this is only the beginning. Those beginning points actually rarely influence a lot in the end of the array. So probably there is some short segment starting in the beginning, and in the end there are some short segments there. So, but anyway, if we are forced to start the segments at 0, 1, or 2, then either relaxing from 2 is optimal starting from some point there, which is the case, or which can also be very usual, actually somewhere there, even earlier than once were more optimal. Because going from 0 to 1 can sometimes be not as good, but going from 0 to 2, like cuts away 2 points already, so that is better than 1 sometimes. So, and here where the stack technique comes. Right? So what we do, let's see, if this is the case, so we would split the segment of 1s in the parent array, then let's look at the first element that is 1. For this element, it is more optimal to go from 1 than from 2, because in the other case, all of this would become 2. So at least one is same, then this one would also stay. So first we check if relaxant from 2 is better for this position than relaxant from 1. Well, the relaxant from 1 is what we currently know for the position, the current value of dynamic. So the thing is, okay, we know that is prime 1 is better than choose must start somewhere later. And we use binary search as before to find this position. If 2 is better than 1 even here, then there is actually never beneficial to relax from 1, always on from 0 from 2. Then we just pop from our stack those ones and just get back as if there were zeros until the end, and only compare with 0, so that we do not have like log squared, because if we use the binary search on the complete array, we would need also to keep tracking at which segment that's not needed. We just use stack, which pop the extra tails that are completely destroyed by the new relaxation, and then when we find the segment that is not completely destroyed, we use binary search to find the exact position when the new segment of more optimal relaxation starts. So the structure of the code would be like this. So this 4J, 0, 2, and -1. We're trying to relax. So while so we have this step of starting position. I will actually leave some space here. You will see as to why. So we say while. Maybe I would better, yes, I would better not leave here, but in the end, okay, while relax from J is better than, okay, let's write a formula, the text. So if while dpj plus cost from J to that position, like the hope force is better, then dp stack top value plus cost stack top value stack top cost. So like this. So while it's better, we just drop the whole segment to the top. Again, be careful, of course, not to pop everything from the stack. It's just the structure of the code, not the actual code that would work. And then binary search from stack top post to n-1 for the new packet point and push it. And what we are, if you look at this code, you see that we update parents, but not updating the DP array. Like, where is this line? This line is gone temporarily because we make like a mass assignment of these parents implemented with this stack, implicitly storing these parents. But we cannot that way store DP. To calculate DP. Fortunately, we know parent, correct value of parent, we can calculate DP. At this point, we know that parent for j plus 1 is correct because we're going to switch to the next value and start from the next j. So we can calculate DP j plus 1 here. Is DP like the current? We need to keep track of where is j plus 1 in the stack, which actual parent is then plus the DP calculation moves here. At this point, we have relaxed from all possible positions. We've chosen which one is optimal. We can calculate DP. So there, a little bit of unusual presentation of this method is that usually you can keep those DP values, and the parent values are actually additional burden to you. So you need to restore the answer and not only the value of the answer. Then you need to store those, and for example, those THT, you need to find not only the value but also the index of the line. Well, usually you do this, but anyway, and store the index of the line. That is actually the parent value for it. Here, it is the reverse. It is parent based. So you keep the implicitly this array of parents. You can actually make it explicitly. And then the value of set here. And you calculate DP when you are sure that the parent is correct. Not you keep the parent when you're the DP. This is a little bit different. I actually really like this algorithm. It is close to THT, but it doesn't involve any geometric things. It just doesn't involve any floating point numbers. So, if I participate now, I would probably use that. Of course, I don't participate, so I don't know, but my teams, they have this in their team. Well, about the formal conditions of that this approach works, let's say you go for 1G, 1G, so it's like, if I remember correctly, like similar to concavity. So like this is always better than this, something like that. For the costs. Don't remember exactly which one should be better. But for squares, I think that my intuition that. Okay, no matter. Please Google them so that we say that, like, yes, something like, maybe I'm doing correctly, somebody is trying to show me, but let's save the keywords that I want because I have so many nice optimizations. Looking forward to it. Okay, so these are all one-dimensional optimizations. What are we going to do now is we are going to consider two-dimensional optimizations. They're actually of different nature. One of them utilizes the same condition that 1D, 1D, but in a slightly less strict form. That is called the monotonicity of the cutting point. And the second one reduces two-dimensional problem to one-dimensional by a clever insight. So let's start with so-called divide and conquer optimization. The question. Augustin, would you write somebody from the organizing team that the microphone started? No,
you can continue without the microphone.
Maybe the batteries are off because it starts fuzzing and then just stop.
Yeah, but you can continue without the
I will
microphone.
continue, of course, without that. I mean that those poor guys on the TV, they would also let maybe here. Cool. Oh, we have another one. This one. Okay, we will switch. Or maybe. Probably. Problem is with the microphone. The whole battery, but I switch to another unit. Okay. Okay. So now let's continue. Back over because. So, two-dimensional problem now. We have at most k segments that we can use. So, as I mentioned before, in this case, it is our benefit is that we can use any order for accessing or calculating the p, because the whole previous line is calculated, and we're calculating the new lines. We have like dp g minus 1, which is completely calculated, and we have dp g, which we want to calculate. Let's again go to the problem of parents, to the previous element, to the beginning of the segment ending at the position I. Another problem to the parents. So here it is. So the optimal value for J for the given I. This optimal value is sometimes called the cutting point because you like cut your data into segments. And the condition of the monotonicity of the cutting point is the following: that parent is, well, actually exactly like there. So parent for G for J minus 1, for I minus 1 is less or equal to the parent for G for I. What does it mean? Let's take this. So suppose that you have processed your formula and now you have the value of dpti and you know the parent. Now you want to find dpti plus 1. You notice that you shouldn't try these values of j, because if they work for our I plus 1, well, the even lower value would work for I. So we should only consider this value. If I do it like this, it still doesn't give the formal optimization in asymptotics, because that would lead to because this would lead to still it would quadratic time if you iterate over all of them, but the first one is open. So every time you still iterate over all of them, but still the first one is open. So you do it random and get a square time anyway. The incorrect solution, another incorrect solution, is to suppose more strict thing that the monotonicity goes like it is like convex, like the concave, so that you go down, 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 and then go up, so at this point you stop, and this is your optimal value. It is both doesn't give, well, it gives actually the linear time because you only move forward, but doesn't necessarily give the optimal value because the function cannot be concave. You see that the cost function is concave, but when you add dp, which actually it is not concave itself, you can get non-concave function. And for example, for this particular problem, the function d cost itself is concave, but cost plus dp is not concave. So moving until while it's better and then breaking is incorrect. Here I should make a remark that especially in older problems, like 10-year-old and older problems, when the judges were not thinking a lot about these optimizations, maybe thinking about other optimizations, the quality of test data can be poor, and this like half greedy method, like going when it gets better and then breaking and going from that point forward on can pass. When we are preparing tests for similar problems now, we carefully choose not to, so that the incorrect solution like this does not pass. Sometimes, unfortunately, some modifications do pass. And then the students start discussing, of course, oh, the judges got such a bad test. Then they get older, become judges, and see that it's not so easy to imagine every incorrect solution that you can come up with. Okay, but anyway, so how do we correctly use the condition that parents are present? Let's do the following. Let's see. It is similar to divide and conquer approach. In some cases, there's a code structure that looks similar, and since the code structure would look similar, this method is called divide and conquer optimization. Although there is actually no divide and no conquer. But the code structure is very similar to that, for example, of merge sort. What are we doing? So let's try to find dpt. Instead of trying to find them in order, let's start with finding dpt for the middle point of the segment. How would we do that? Well, okay, we would iterate over all possible variables and find some optimal values of the parent of m points here. Now you see that for the positions to the left of M, the parents are to the left of parent of M inclusive because of this condition. And for the positions to the right of M, the position for the parent is to the right of the parent. Inclusive again. So we recursively now process two segments to the left of M and to the right. Again, we take the middle of the segment, find the parent, and take the middle of this segment and find the parent. And here we go until here only, but if the parent of M was somewhere like that, then at this position we will only go until this. And for the right part, we already see the optimization here because we do not consider possible parents to the strictly to the left of the parent. How does the code structure look? So it's like update left right. So again, we take M, and we also have parent left, parent right. So we take M in the middle. We find the parent, iterate J for J from parent left to minimum parent right M. This would be parent M. And now we make two recursive calls. Left and minus 1 left, PL, and like I think here is M, if not included, here M plus 1 R M. Like this. No, and of course you need to terminate the recursion in the segment example. So this is the code structure, and since it's, well, this can be in some sense considered as divided stage of divided control, although actually there is no explicit division of your data. And the conquer step is not divided. So only the code structure follows the divided and conquer pattern. The actual divide and conquer, I don't just. Okay, so this is the first way to deal with two-dimensional problem equation. Please.
I don't understand how you keep the solution to, like, you start two new segments and too far apart of the.
Yeah, well, so you see, here you pass the possible ends of the segment that contains the parent for the all elements of this segment due to this inequality. So initially you like pass update of the whole from 0 to n, from 0 to n. And when you are calculating your dynamic programming using the recurrence here again the backward recurrence as we started with. You are only considering J not. The formula says dp Ti is maximum minimum. Minimum for J less than I of dp T minus 1 J plus the cost. So you're iterating not all possible values of J, but only from PL to PR, but of course you shouldn't go to the right of them. What is the complexity of this approach? Let's see. The depth of recursion is logarithm, and at any depth, there are actually two possibilities. Every possible parent, if it is not the ending point of the segment, then it can only be considered at one segment, because like at level 4, for example, at level 3, for example, when there are 4 segments, there are parents that divide this possible parent segment to another 4 segments. This is only considered for the first, this is for the second, this is for the third. And the ends of the segment, they are belonging to both, and actually sometimes can belong to more than one and more than two segments, because they can belong to just one element. But every such element just terminates or starts the cycle, so again, there is a linear number of such events. So the total number of values considered as parents is linear at every depth of the recursion, so the total time is total time is n for every level of recursion, so it's n logarithm n, and of course for every t we have the separate algorithm, it's k times n times logarithm n, which is better than k times n squared for the names. Now about the proving of the monotonicity, proving of this. Oh well, you tried using your intuition, or maybe if you're the problem setter, then of course you have to start to write all the formulas. Okay. Now another approach. This approach keeps the problem two-dimensional, just changes the order in which you are calculating the values so that you get the better time complexity. Another approach reduces the problem to one-dimensional with a smart trick. Let's see. Consider again two-dimensional problem. And let's try to find any solution to our problem. So, suppose we have found the solution, and let's say that we use not less or equal to k, but exactly k segments. It will be a little bit easier to describe, but similar approach works for no more than k. So, suppose k. Let's solve the problem. If we were so lucky, then the solution to, let's solve one-dimensional problem. Let's ignore this condition and just solve the problem. Consider that we are lucky and we've got the exactly k segments in our solution. Okay, is it possible? Well, at least there is at least one k for which it is possible. Yeah. If it is, then it is, since it is the best solution over all possible solutions for any k, then of course for this k this is also the optimal solution. So, but what if we are not lucky? Suppose that our solution that we have created contains more than k segments. Actually, for one-dimensional problem with small values of c, it is sometimes more beneficial. It is beneficial to have shorter segments. With a big value of c, you have longer. So suppose there are too many segments in the solution. Let's do the following. Let's add to this cost some constant value. I will call it lambda. It actually goes from calculus, I think, where similar approach is used to minimize function given some constraint. So, it's called lambda. I don't remember some mathematical like Lagrange. If you were studying good maths, like first or second year of studying calculus, you will get that to optimize function given the condition. So this, the guys have seen the similarity between these two approaches, so they named it lambda. Although it is a little bit different, but okay. So let's add lambda to this cost to make segments more expensive. Since we are making segments more expensive, it is more beneficial for the one-dimensional problem to create the solutions with fewer number of segments and with fewer segments, and maybe if we choose correct if I have guessed the correct lambda, then the solution for one-dimensional problem will give exactly k second. If it does, then let's see. It is the optimal solution among all one-dimensional solutions for this new updated cost function, where cost of the segment is increased by lambda. But among all possible solutions with exactly k segments, compared to the initial cost of these solutions, the cost has increased by lambda k, which does not depend on the solution itself. So our optimal solution for new one-dimensional problem is optimal among all solutions for this new one-dimensional problem that contain exactly k segments, because it is optimal among all, and in particular among those. And since it is optimal among those, and all of them have changed by the same value, then it is optimal for the original problem as well among those solutions that contain exactly k segments. So this is the possible. So if with this lambda we have the correct solution, the optimal solution that contains exactly k segment, then we have done, and we have the optimal solution for the original form. If there are too many segments again, we should increase lambda even more. And if there are not enough segments, then we have created too many big lambdas, and so we should decrease lambda. Actually, this can even happen initially, that sometimes the initial solution is too few segments, so you would like to make more beneficial to use more segments by maybe using negative values of lambda to make the one-dimensional solution use more segments. Okay, now it's easy to see that we would generally like to use binary search. So the monotonicity of the number of segments for reasonable cost functions seems more or less obvious, because the more you add, the more expensive becomes each segment, and the better is to use fewer segments. The problem that we can that can occur to our approach is that for some lambda we have like k minus 7 segments, and if we like decrease lambda a little, we had like k plus 2 segments. Oh, exactly. Let's see why can it happen, and what is the condition that it never happens, and what is the solution if it happens, but the function is still good for lambda optimization. There are such cases. So what I will do, I will again refrain to geometrical interpretation. Let's build the graph of the function. Here is k, and here is cost of two-dimensional problem. Two-dimensional, I mean that with the constraint on k explicitly given. Exactly. Okay. So suppose that we're allowing one segment. Probably it will be some like expensive solution like this. If we allow two segments, probably it will be a little bit cheaper. Or three. Then actually this, at some point the C starts to matter, and then it starts growing, because this C overcomes this square member. So at some point we have the minimum of the one-dimensional problem, and then it starts to grow because C starts to matter. So the length part still continues to increase, but the constant now is more than the decrease. So, although it decreases, the decreases adding this constant forces it decreases. Okay, how would this? Let's ignore this inclusion part for a while, because plus c and plus lambda are the same. So this plus c and plus lambda actually do the same thing. So we can just like shift our lambda a little bit, and this gives the same. Well, so let's ignore this for a while. And in this case, if it's only length square, then it goes like this on and on and on, and it decreases. And finally, for n segments exactly, we have the zero cost, which is because we cover each point with this zero length segment, only the length. Now, suppose that we are having some lambda, and let's calculate the cost. Well, for this point, what is this point? Its x coordinate is k. How many segments are used? Its y coordinate is actually, we make a solution like this point is k dp k n. Yeah? Exactly. Its y coordinate is the answer for this number of segments. So if we add lambda, then for these particular points, the cost of one-dimensional solution would be its y plus k lambda plus x times 1. So this would be, so you see, what we're gonna do, we want to find the optimal solution for exactly k segments. So what we want to find is we want to find this. Of course, if we calculate two-dimensional dynamic programming, and we get all these points, and we can choose, and in particular this one. But when we are working with lambda optimization, we don't know these points. What we do is we choose the value of lambda, and then we choose the point out of this. The one-dimensional solution gives one of these points. Which one? The one which has this value minimum. From among those solutions with the same number of segments, it always choose originally optional because the added value is the same. But from among different values of k, well, it chooses the one with this minimum value. So, consider that this value is x plus y plus x times lambda is some ans 1d. And we rewrite it in our quite familiar choice form, like y is equal to minus lambda x plus ans 1d. And we see that this is the line, high school line, with a slope of minus lambda. And all lines in the form of minus lambda plus c have this are parallel to like such line with a slope of minus lambda. And from among those lines, we are looking for the one with a minimal ans 1d that passes through one of these points. And so if we start from minus infinity and move up such line, the first point that it hits is exactly the one that gives the one-dimensional optimal solution. And what we want is that it would hit the k point with the x coordinate k. And the change in lambda actually does the rotation of this line because it changes in slope. And from here we can see the requirement for the problem, so that lambda optimization with binary search always gives the correct solution. So the easiest would be if this function, two-dimensional solution of k, is strictly concave. So in this case, there is always such value of lambda that this and only this point is optimal in this direction, or to an alternate side. So, in this point would be hit, and the binary search always find exactly k. So if it is strictly concave, strict concavity means that increasing the number of segments, or I don't know, in general setting is usually called batches. Increasing the number of batches by one gives strictly less benefit with every new batch. So this, we go by one here, but every time we move by a smaller amount down. This is an optimistic situation. It's not always the case actually. The less optimistic but still approachable situation is if it's non-strictly concave. So if the adding new batch decreases the cost by the same or smaller amount. In this case, there are situations unfriendly to our solution that there are several, like the one shown here, that there are several points on the line with the optimal lambda, and k is not the ending point of this segment. So in this case, the 1D solution cannot generally find exactly k. It can find this or this. It will, well, if you write 1D solution, the relaxation code uses either less or equal, and you are iterating or increasing or decreasing the segment length, and based on these conditions, you would usually find either the maximum or the minimal possible value of k for this lambda. It will be automatically, you don't need the secondary optimization, you generally would. And if in a more complicated course, you can sometimes find just a random of those. There are now two nodes on this. If the optimal, if you only need the value, you don't need to restore the answer, then that's not a problem at all. So suppose that you run binary search on lambda, and like you find the maximal lambda so that the number of segments is at most k. Yeah? So in this case, you will probably hit the maximal lambda, maximal like this. So yes, so you will probably find this way. Okay, so you found you cannot make better. If you rotate it more, then it would already be this. Oh no, then it would already be like this, smaller than. So what should you do? Okay, you have this k prime from your binary search. You have your required k, and you know that this k is on this slope. So going with the slope of lambda, you will actually reach this point you just. So now your answer for k is answer for k prime minus lambda k minus k prime. So you just make this visualization and move along this lambda line. The problem is getting worse when you need to restore the answer, because you can find the solution, you can find the value, but how do you find the solution with exactly k segments? You know how to find with k prime. If you rotate your line more, you will get with it like next value of k, but with exactly k, it's not clear. Well, first, honestly, I didn't try it myself, but I know people who have tried it. It usually works. What do? You want to find the solution. So you know the correct answer. You know k, and you know you have one-dimensional solution. So for every one-dimensional solution, for your one-dimensional dynamic programming, you store not only the value, but also you find the maximum and the minimal possible number of segments for the solution. So when you make relaxations, if it's less, then you update with the new value and set maximal and minimal with maximal and minimal for this plus 1. And if it's equal, you do not change the value, but you update with the maximum and minimal of this plus 1 as well, relax and minimal and maximum. And when restoring the solution, you're starting from here, and you're looking for such, you're going back, looking for the first possible segment plus segment that leads to the optimal solution. So its cost plus the dp there is still gives you the optimal value, and you can stay, your current required number of segments minus 1 fits into this position's segment of minimum 2. This approach requires that the number of possible segments for the optimal solutions form the segment. The number of possible batches for the optimal solution form the segment of values. This is the case for the final situation because of this lambda slope and the concavity. But it's not absolutely clear, of course. It is also true for all intermediate values, but the intuition gives us that it must be the case as well, because should we stop there, why would points after that influence this position anyway? Of course they should. If the function is concave like this, then of course it is concave for intermediate values as well. So this form the segment of possible batch number count of batches in the optimal solution. And then, so again, you go back until you find the possible last batch that first gives the correct solution. So its cost plus dynamic value, dp value here is optimal here, is equal to the optimal value here, and your new required number of segments before using the batch, like required here minus 1, fits into the segment of possible number of batches in the solution for this one. And from what we have discussed in the intuition level, you should always be able to find such step back. And it's totally linear because as soon as you find it, you jump here and start looking from here, so you never actually complex. The restoration of the solution will be in the linear. It's not that easy actually to do if you do additional optimization for your one-dimensional problem. You don't usually have just lambda. After lambda, you get one-dimensional problem, and of course, that one-dimensional problem you also optimize, like with 1D, 1D, or with CHT, or with the chow, and so you need to introduce this minimum and maximum into that. For example, for the CHT, it requires quite careful moment with multiple lines passing through the optimal points, because in this case you will need to consider them all. So I haven't seen actually the problems where you need both optimization of 1D, 1D after of one-dimensional problem after lambda and restoring the solution. So I have seen the problem when you need the answer, and you can update it with this formula and double optimization. First lambda, then some one-dimensional. I have seen the problem when you need to make lambda to get rid of the two-dimensional solution, but then more or less naive solution and answer restoration of the two-dimensional problem. That I've also seen. The most deadly component I haven't seen, but I believe in some Chinese contents, they must exist. Okay, are you? The last one for today. It's gonna be now so-called Knuth optimization. This is another variation of monotonicity of the cutting point, but for alternative setup. All the problems that we have discussed so far, actually we have discussed it on the example of one problem, but there are a lot of problems of this type, and good forces at least 20 is a very low estimation, 50 maybe. Like they have this dynamic programming for some split something into some batches with some conditions, and you want to maximize or minimize something. And then, depending on that something, you can use one of the optimizations. But there is another type of programs that are not so-called prefix dynamic programming programs. What is the prefix dynamic programming? Is it that here, the state of dynamic programming is the prefix of our data. So you just have processed some I first points, like I first objects, I first whatever. Sometimes you have a so-called segment dynamic programming when the state of the segment is the segment. It is, in some sense, we also have segments here with their costs. But these segments themselves are not our point of optimization. They have their cost, which is given from the problem state. But sometimes we need to optimize the segments themselves. The most classical problem on this is given in Corman and others when introducing dynamic programming. There is a matrix multiplication problem. Maybe you've seen. Are you using Corman and others? I don't know. Corman, they just understand. CLRS it is called. In American universities, how is it called in New York? You said, no, in Russian it is called Corman for the first name, or name of the first call. So, how is it called in Latin America? This book. Just Corman, like in Russia. Okay. In America, in the United States, they respect all the others, so they call it CLRS. Okay, so if you open dynamic programming chapter in Corman, you will see the matrix multiplication problem, which is actually the segment problem with the segments as states. The matrix multiplication problem, unfortunately, or maybe fortunately, I don't know, doesn't allow for Knuth's optimization, so we will consider another problem as an example. This problem is statically optimal binary search trees. What does it mean? Binary search tree is a tree that stores values, the keys in its nodes, and the condition is that all the keys in the left subtree are less than the key in the node, and in each is less than all the keys in the right subtree. So let's draw this. Like for the tree, and for every node, not only for the root, but for every node, its value x, and here we have greater than x, here we have values less than x. So this is called binary search tree. There are actually many approaches to make this binary search tree balanced, like red-black trees in STD set, or STD map, like trips that we have discussed in the persistent setting that we are using, and if we need something that STD set doesn't know, that cannot do. Or there are some other approaches like AV options, many options. What we will consider is statically optimal binary search tree. Consider you have the set of keys, and you have the frequency values for the keys. So there are keys x0, x1, x10 minus 1, and each key is associated with its own frequency value f0, f1, x1, f10 minus 1, which gives us the frequency that this key will be retrieved from the tree. And since actually there are multiple possible structures of the tree for the same set of keys, you can choose to make keys that are more frequently retrieved to be closer to the root, so that they're even faster retrieved than logarithm, because the root key is immediately retrieved, and the leaf key is the logarithm time if it is balanced, and up to linear time if it is unbalanced. So the function that we want to minimize is sum for the substructure of the tree, the frequency times height depth, yeah, times depth of the key, yeah, for all the keys. This is what we want to minimize. Why is it called statically optimal? Because the keys are not inserted or removed. The keys are given beforehand, and you can create the static fixed tree to make it optimal. If you are interested, by the way, the dynamically optimal binary search tree is a well-known problem that is not completely solved yet. There is a hypothesis that splay tree that is used in Latin countries as well. That splay tree is dynamically optimal up to multiplicative factor, but it is, well, last time I checked, like a few years ago, it was not proved. So there is some progress on this, but not proved yet. But for statically optimal trees, the problem is solved by Knut and others, and it is easy, and it shows us the last optimization for today. So what do we do? How do we solve this? Okay, the keys are go like this. So we choose one key as a root. After that, what we do? For the root, that would be just its f root times 1 will go to the answer. We know which keys would go to the left subtree. That would be both from 0 to root minus 1 inclusive. And we know which keys would go to the right subtree, all the others, from root plus 1 to n minus 1 inclusive. Because the order of keys corresponds to their order, the order of keys in this sense is fixed for the binary search tree, for the definition of it. So, and for those, we will have the same problem. The difference only that the depth is one more, because they form their own tree, but the depth is plus 1 because of this root. From among the structures of different structures of these trees in the left and right subtrees, there is a constant added factor, constant term that is added to this value, which is the total frequency of this, because all their depths are increased by 1. So in this formula, this is just the total sum of frequencies will be added to this formula, and it doesn't depend on the structure of the tree. Therefore, we have the same problem for these two subtrees, and they can recursively be solved. So we get the following dynamic programming solution. So the dp from L inclusive to R not inclusive is the optimal, the cost of the optimal tree on the segment from L to R, and we choose its minimum for the choice of M as root, L less than equal than M less than R. We choose M as the root, and now the cost there will be F root plus FM. DP from L to M. Let's use brackets, not in use like DP from L to M plus DP from M plus 1 to R plus, actually, again, for this DP, all the nodes here are one deeper than they would be like, so it would be like plus sum for I from L to M minus 1 Fi. And for this DP, again, all the nodes will be one deeper than they are in the solution for the segment. So it will be from I from M plus 1 to R minus 1 Fi. And if we look, we see that actually all the F's are summed, one for the root, and also all in the left and all on the right, so it can be simplified with minimum for M, dp L M plus dp M plus 1 R, and plus the sum of all Fi, which is not dependent on choosing of M. So now what, if we use direct approach, like naive solution to this problem, we would get n cubed. How can we improve? Let's see. Suppose that we add the one key to the segment. There are actually two options. One is that it is optimal to add this to its right subtree. Question, sorry?
You not need to subtract f of m in the minimum because of you summed everything.
Yes, so you can move all the sum of all f's out of minimum because actually all f's are summed exactly once beyond the dp range.
Yeah, but
f of m is not included in the left subtree, is not included in the right subtree, but is included in the root. So it turns out that if it were not, it would not be a big of a problem. We would write here minus fm, or maybe it would be. But it is. But here it is not. So let's get back. So now, either we are added here, or maybe the tree will be restructured completely, and the root will be. It will be optimal to choose another vertex as a root. Which one? The monotonicity of the cutting point in a similar way as in one-dimensional problem here. In the prefix problem here, it was like this two-dimensional but prefix. It says us that the root will only, that it is not possible that the optimal solution will have more actually nodes in the right subtree, and the root will be the will have the lesser index than if we didn't have this element. Where it's taken, that means that this root for the segment of LR is less or equal than root, optimal root for segment LR plus 1, and similarly less or equal, if you add it to the left, should also be considered root for L minus 1R. So this is the monotonicity of the cutting point for the segment dynamic programming. And if this condition is satisfied, again, of course, it's not easy to prove directly. You can, this time I send you either to the Knut book itself, which I don't think anybody will be able to read completely. It's very long. Or to some other internet sources that analyze this. And how can we, if we believe in this inequality, how can we utilize that? Our idea would be the following. So instead of going by, like, already here, it's interesting that we need to choose the order in which to evaluate these values, because both for the same L and smaller r, and for the same r and greater L, there are references to other values of the integral. So you need to go by diagonal. So you just iterate over the length of the segment that you want to evaluate, and then with a segment of given length, all the shortest segments are already calculated, so you go no matter in any order for L or for R. But here, this particular inequality refers to longer segments. So this is kind of a contradiction, but we just rewrite it. We reiterate this equation, making R plus 1 SR, and this would be R minus 1. So we see that root of L R minus 1 is less or equal than root of L R. And here we say this is L, and this would be L plus 1. So this is less or equal to L plus 1 R. And with this reformulation of this inequality now, it already refers to roots of two shortest segments. And this way we can, again, in a similar way to this divide and conquer approach, when choosing which root to choose, here we instead of this, we use root L R minus 1, this root equal to M, this root equal to the root of L plus 1 R. And this way, it can be seen in analog to this, that every possible value of M will only be considered as a root, but either once if it's strictly inside this segment, or maybe multiple times if it's the end, but for every segment of such length, there are only two such values of m's that are its ends. So the total number for given length of all considered possible roots is linear, and there is a linear number of lengths. So this gives us m squared time this optimization. Okay. Actually, there are not very many problems for this optimization. Unlike previous optimizations, well, I know kind of 3 or 4 problems that utilize this optimization, but sometimes the problem setters read the closed book and say, oh, this is a nice thing to put into the program. And it is, and I haven't seen this. Because again, I say that there are a few such problems. So they create. So from time to time they happen. I think maybe even at World Finance some year there was some. Well, okay, at this point, thank you for listening for today's lecture. If you, before going to lunch, one last note, if you want a simpler contest today, please write me on Telegram your team login name. I will write in Telegram a message with your team login name and the message that you want a simpler contest. And I will, in exchange, send you the link to the mashup and platform. And if you're aiming for a world final, then you should not do that. You should solve it. Okay, so have a good lunch.